is what you get. If you don't hear me, please come down closer. There are some seats down here as well. Okay, so good morning and welcome to day 2 of ProbAI. Today it's the Variational Inference Day. It's me and Thomas who is sitting there who will be running the show. We've done this for many years, and usually we have Andres with us as well. But since he got this fancy title of his, then he refused to be part of what we slaves do for him here, so that's nice. As Andres said, it's going to be like a full day where we are doing batches of slides and theory, and then you get to try it yourself with hands-on notebooks after. And this is going to go back and forth. But what is going to also happen is that we are building step by step here. So if I am going too fast here in the beginning, you will have a really boring day after, because then you kind of lost the train when it left. So please stop me if I'm talking too quickly. We have too many slides as always, so we kind of feel like we need to go very quickly through them. And that might be unhelpful, so then stop us rather, and we will make adjustments as we move along. Okay, so variational inference. This is a deterministic way of approximating Bayesian inference. So this has been around for like 10, 15 years maybe now, and when it was first picked up by the community, then everyone wanted to use this because it is very scalable. So we can efficiently, quickly do probabilistic inference in models that are so large that we previously couldn't. And then people generated cool plots like these showing high-dimensional data being analyzed with probabilistic methods. These plots are now so common that we don't really care anymore. The new kind of vogue, I guess, is generative models. And also here, variational inference has a central part. So this technique is a main tool in the toolbox for probabilistic AI, and that's why we have set aside a full day for talking about this thing only. Yes, so what we're going to do now is kind of step back a little bit and start with the motivation and see where that leads us, and then we will dive into how variational inference works. So whenever some of us is doing like a desktop machine learning task, then we download some highly curated and nice data. We do take some random model from our toolbox, run and see what happens, and then at best tell some friends about the results, but it doesn't really matter. On the other hand, when you are building a real-world application, then suddenly it's a completely different kettle of fish, because then there are stakeholders that actually rely on the results, and we need to be more careful. So there might be interest in the modeling. How are we representing stuff? Are we able to incorporate domain knowledge? Can we be transparent about what happens? Can we handle problematic data with, say, missingness or latent variables, high noise, low signal? Can we scale? Is it robust towards outliers, auto-distribution? Can we do adversarial attack defenses, and so on and so forth? So we need to be careful about the model suddenly. And since this here is the probabilistic AI summer school, the solution is, of course, to do probabilistic framing our machine learning model. So this is what we will do today as well. We will build probabilistic models and then do probabilistic inference as the, say, answer to the learning task that we are faced with. And not only are we doing probabilistic machine learning today, we are taking it one step further and doing Bayesian machine learning. So what that means is, of course, to have a probabilistic model and a prior over our parameters in this setting. So we have a likelihood part telling us like how the data relates given the model, theta. And then we have a prior telling us what we believe about the model before we kind of start. So that's P of theta. So I'm going to use theta here as a representation of the model. Think of that as parameters within some flexible model class. And then P of theta might be informative or clever prior, or just like a very vague thing. It doesn't really matter for the arguments that we are going to do as we move along here. Okay, but when we have this, we can of course calculate the posterior over the model, given the observations that we have. So I'm getting now calligraphic D, this is my data set, and then I can calculate the posterior for my model, as I always would, using Bayes' rule, like this. So now this is my object of interest here. This captures everything that is to learn from the data about my model. And when I have that, I can use this, for instance, to come up with a predicted distribution, like this here. I'm integrating over my uncertainty about which model is the correct one. So this is represented here, and I'm integrating over all possible parameters, or all possible thetas. This gives me now the predicted distribution for a new observation, x prime, given the data that I have. All is good. We have seen this many times before. But just to hammer it really in with notation again, this is what we mean by Bayesian machine learning. So what happens here is I am maintaining a distribution of a theta. So I'm not only like playing around, I am really representing my uncertainties about which model is the correct one, this part here. And that's why it's a Bayesian machine learning technique. If this distribution at some point is degenerated into a single point, then it's still probabilistic machine learning, but not Bayesian machine learning. Okay. So let's try to do Bayesian machine learning. And as everyone all the time, we will do linear regression. This is a very simple model, and we like it because it is analytically solvable, also in the Bayesian setting, so that's what we're going to do. So I am now looking at a univariate response, y, from a univariate explanatory variable, x. So I am believing in a model where yi is observed with mean w0 plus w1 times x, and with some observation noise around it. Okay, so I have some parameters here. w0, the offset, w1, the incline in my regression line, and then sigma y as well. But that last part I'm going to assume is observed. So that means my uncertain or unknown parameters are these two guys, w0 and w1. And then to keep faithful to my notation here, we are going to call that theta. So theta is now the weights, w0 and w1 in my regression model. And I am doing Bayesian machine learning here, so I need a prior, and for better or worse, this is a silly and fairly naive prior. Just put them at 0 and some noise around, and then see what happens. So this is my prior. Now, what can I do? Well, the joint over my data and my model, this one here, is a quantity that we will have lots of use for today. And it is straightforward to put it up. It's just the product of the likelihood and this part, and the prior, this part. So what happens here is basically that the likelihood term factorizes given the model theta. So this is a product of all my observations, and the prior comes in front here, and that's all I need to write down this thing here, the joint over the data and the model. So far, so good. Let's see how it works. So now I am learning a model with some fake data observations, these 5 observations here. So for each of these x values, I have sampled a y value, and this is the data set. The data was sampled from this model. So the offset is 1, and the incline is 0.5. And then the observation noise is fairly small, whereas the prior is extremely vague, as you can see here. Okay, so what do we do? Here I have shown 2 results in this plot. The blue contour lines here give me the posterior distribution over offset and incline. So this is a Gaussian. It is negatively correlated, so high values of W0 would give me smaller values of W1 and the other way around. And the mode of this distribution is here. This is the map estimate. So if I'm asked to come up with a single estimate from this distribution here, what I'm going to do is to take the most probable model under this posterior, which is the mode, this point. And that is shown here with this red line. So what can we think about when what can we say about that model? Well, it is reasonable, isn't it? It's passing through the data okay. We don't really have a model uncertainty thing, so it's not Bayesian machine learning, but it's kind of okay. What we can do with the Bayesian model, though, is to sample many candidates. And that's what happened here. So each of these blue lines would be a candidate model, sampled from the posterior. So any blue line here is a potential mean for the model W. This model, yeah, it's not even here. The model for how Y and X interacts. So basically, you get the line here by sampling a W0 and a W1. The W0 would be the offset up here, and the W1 is the incline. And we can see here that we have negative correlation. So when I sample a W0 down here, for instance, which is smaller than the average, which is 1, then I'm going to get more steep line. If I sample a W0 that is higher than the mean, which is, say, 1.2 or something, then I'm going to get something that is not as steep as the other lines. And this is then giving me this crossing pattern where they more or less cross at the middle here. So here I get more like a feel for the uncertainty that I'm confronted with. I don't really know which model is the best one, since I only have 5 data points. And this is captured by the Bayesian setup. On the right here now, we have the predictive distribution. So the question here is, what would be expected if I'm going to sample again at x equals 1? The map model is just choosing its mean, which is up here, more or less 1.45, I guess, and then add the observation noise around it. So this goes in here. Fairly peaked. Doesn't really reflect our uncertainty about the model at all. And we can see that the observation that we already have at this point, this guy is considered to be really, really unlikely under this predictive distribution, which is kind of a quick test of that distribution not really making much sense, I guess. It is too narrow. The Bayesian posterior predictive is the blue thing here, much wider, capturing the observation we have, capturing the true predictive mean, and so on. So more able to capture the uncertainties that we have. Okay, so this is then kind of the point of being Bayesian about machine learning. So to summarize all this, what we are going to do now is to try to do Bayesian inference all the time. So we are constantly searching for this thing here, the posterior, over the model given the data. This can be solved sometimes analytically, like for the linear regression model. And when that is possible, then all is good. But mostly it's not possible. And then we need to do something else. And that something else is going to be to try to approximate the true posterior distribution. So we will try to do this now using optimization. And we are looking for a technique that is computationally efficient, well-behaved, and can be integrated with other frameworks, like, say, deep learning stuff. So we are not going today to talk about sampling. We are not going to talk about degenerate solutions like this map thing. But we are trying to do something that captures the full distribution, P of theta given D. And then we will have this assumption here coming with us throughout the day. We will always assume that even though we cannot calculate this guy efficiently, we can always calculate that guy efficiently. So the joint is available to us. the conditional or the posterior is not. And the reason for this is, of course, that this integral here is hard to come up with. So that's the problem. That makes it hard to come up with the posterior. So we will assume that the joint is there, the posterior is not. Okay, so I was told to repeat questions, and now I'm going to do it because I'm a clever kid. Why are we doing this and not sampling? So there are different use cases. This thing here is wrong. So we will approximate stuff, but we don't have guarantees that it is going to converge to the right solution if we leave it forever or stuff like that. So we are deliberately making mistakes here. It is typically quicker though, so it is a trade-off. Sometimes you will do sampling, sometimes you will do this.
But the difference is if I'm not worried about the execution speed, I should just
So if you don't care about speed, then probably MCMCU would be just as useful, if not even more useful. I agree. Yep.
And one question for a few slides back when we talked about the linear regression problem. Normally linear regression can calculate like your uncertainty about your parameters in the distribution, and then have like some uncertainty about your predictions. Would those be identical to the ones we get under the Bayesian approach, or would they be more restricted?
I'm not sure if I understand the question. So you say that you would, if you're not doing Bayesian setup, you still can come up with confidence intervals, for instance.
Can you do like maximum likelihood estimation, but then we can calculate some standard deviation on the intercept and on the bias, and then have some uncertainty about our predictions. Is it identical to the distribution we get under Bayes, or different?
I think it will be different because here we are using priors as well. So there is additional information, and also the use case would be different because what you would do with your confidence intervals in a frequentistic way would probably mostly be to say that, okay, this thing here is not significantly different from 0, so I don't think that there is an interaction between X and Y. But here it's more like representing your uncertainties and utilizing that downstream for your decisions after. Yes.
Which is better, and where can we, where it is, because I believe that there is also this thing that the variational inference could overestimate the modality or underestimate the modality depending on how we use it. So
yes.
What are the caveats?
Yes, we are going to look in detail on those problems now. So as you say, the variational inference technique is making assumptions that we know are wrong, and those will result in underestimating the uncertainty of your posterior, which is problematic or can be problematic. So then this needs to be considered. But the sales argument here is, as far as I can see it, always speed and convenience and general purpose type framework that is efficient to implement also. So that's how I see it, at least. Thomas, do you have any additionals? No? Good. So let's then meet our new friend, the variational inference. So, okay. This plot here is supposed to kind of give you the whole story of what is going to go on. So what's happening here is we have a true posterior in blue here. This is the model that we would try to approximate. Then to do that, we are first defining a family of approximations that we like. in this setting here, this plot, when I was made, I think Thomas made it by having a mixture of Gaussians here, and then the approximation family is just any kind of single mode Gaussian, so no mixture Gaussian. And then the question is, how can we approximate a mixture Gaussian, specifically this mixture Gaussian, with a standard Gaussian? So that's our family of approximations. And then we have lambda here, which is kind of an indexing into this family. So our task is to find that lambda that gives us the best result. So we can think about lambda as a parameterization. So here the mean and the standard deviation for that Gaussian that we are going to choose. So then the problem of variational inference is kind of an optimization problem where we are looking for the parameters lambda that are best, kind of. And best here means that we want to have something that is close to the target, whatever that would mean. So this is kind of the plan. Find out what this means in mathematical sense. But keep this model or picture here in mind. What we are doing is trying to find an element from this family that fits with our target. Okay, so notation first. We have this thing here, P of theta given D. This is what we are looking for. So we will use P for that distribution, and we will use Q for the approximation. So anytime there is a Q, it is an approximation. Anytime there is a P, it is a, say, true model thing. We choose the Q based on data. So we are sometimes, or most of the time, actually not bothering to write Q of theta given D. The given D part is implied. So I'll just say Q of theta, and then everyone knows it's given D anyway. And then setting out what we need now is to find the parameterization that indexes this Q set here, so that we find the element Q in the set that has the minimum distance from the target. This is the target. We'll just find them, the guy in the set that is closest. But for this to make sense, we need to define what we mean by closeness. So what is the distance here? And particularly, it's a problematic thing because we need to calculate the distance between a candidate and the gold standard, but we don't know what the gold standard is. So how do we then calculate the distance to something that is unknown to us? If we know what this is, we don't need to do this in the first place, right? Because then we know it. Then a second problem is, what do we mean by this set of candidates? So we would like to have a flexible set. If this candidate set only consists of one specific model, then it might work, it might not work, but who knows? And it's kind of meaningless, the whole thing. If it's too flexible, this set, then we might come up with an optimization problem that is too hard to solve, or we might find a solution that is intractable and not useful for us afterwards. So we have to kind of balance this when we are defining what set we are looking at as well, the candidate set. Okay, so two problems that we need to look at. First, the distance. So if we look at this from a mathematical point of view, then this is a field of science in itself. What does it mean to make it, to define the distance? What can we use the distance for? Metric spaces, all that. And then for distances, we typically see three requirements. So first one is positivity. So the distance from f and g is always non-negative, and it's only 0 if the two elements f and g are the same. Then people talk about symmetry as important, saying that the distance from f to g should be the same as the distance from g to f, which makes sense. And then finally, the triangle inequality, saying that if you are measuring the distance from f to g, it can never be shortened by having to go through h on your path from f to g. So these are the typical requirements for metrics. Yep.
Lost on this distance thing. Can I ask you to go back to the slide and just
Yes, so by tractable distribution, we mean that we want to find some solution here that we can work with. So that we can work with. Oops, sorry, I forgot to repeat the question. The question was, well, first part was what do I mean by tractable distribution? And the point there is we want to have a set of candidates that is so that we can quickly go through it and find the best candidate in there, and that this best candidate is something that is viable for further use. So it's just a silly way of saying that this set Q needs to be well defined or cleverly defined. And then regarding distance, here first we are trying to approach this in a fairly general way. So there are some objects here, let's just measure the distance between them if we can. But what this ends up with is that there is a specific way of doing this, which is the Kullback-Leibler, which is the way that people are then typically calculating distances between distributions. So this is kind of just a general thing saying that, okay, these two are objects. We have distribution 1, distribution 2. Why not have some way to calculate if they are similar or not? And this is one way of doing this, or the most used way, I guess.
Maybe a summary of how do we use something that we don't.
Yes, how do we compute the distance between things when we don't know it? This is an important problem that we will solve.
Metrics also that are used between the probability distributions, like process time metric or something like that.
Yes, so people have been trying to, so yes, so are there other ways of doing this? That's the question, I guess. So what we use here is the Kullback-Leibler, and this is kind of the choice that leads to all the cool things. Other choices are available, kind of. But for this purpose here, we are going to do Kullback-Leibler. And this is a semi-cool good choice in the sense that it's not a metric, it is not symmetric, and it is also not obeying the triangle inequality. And this makes us see some strange behaviors that you will see an example of very soon. Yeah.
If we use Probabilistic and therefore non-symmetric, not metric but distance measure, is there any reason why we then normally choose, is there any reason for the order we choose, like do you P, Q or Q?
You are my favorite guy. This is the next slide. Such an excellent way of transporting me into the next slide here. So yes, there is a difference between going QP and PQ. And now we will look at those and see which one is meaningful for us. So as we noted, Kullback-Leibler is non-symmetric. So we have to think about whether we are going to do the distance from the approximation to the target or from the target to the approximation. So let's just consider what these two are and how they differ. And here I have a cheat sheet at the bottom, so defining what the Kullback-Leibler is, what entropy is, and also here there is a piece of intuition that you will need, and that specifically relates to how things behave when they go to 0. Problem is this part here. If this guy is 0, this is minus infinity plus infinity, right? So if this expectation operator gives any mass to the area where this guy is 0, then the expectation is going to be plus 0. The Kullback-Leibler is large, meaning that the distance is not going to make these choices of distributions fit together, kind of. So that is the intuition that we will use. Okay, so let's start with this guy, from Q to P. Then I've written out here the Kullback-Leibler, what it relates to, and remember that it's now the Q distribution that we are optimizing. The P is fixed. So for this one here to be good, we need to make sure that whenever P is large, and therefore log p is large, this is where we would like our expectation operator to zoom in, right? So that means whenever p is large, it's good to have a large q as well. So q probability is allocated wherever there is a region that has high p probability. And then there was this thing about the zeros. So if this guy is 0 or close to it, then we must make sure that the expectation operator is not looking at that area. So that means if p is 0, q must be 0 too. And then finally, we have an entropy here with a minus in front. So that means high entropy is good. And you can think about entropy as more or less variance. If you're not used to this term, then it's the level of, say, uncertainty in the distribution. So high variance. These are the three things that signify Q distributions that are close to P when the Kullback library goes from Q to P. If we swap this around and go from P to Q instead, we get this representation here. Again, we would like to have high Q probability in the areas where we have high pre-probability. This is because then the expectation here will focus on the areas where P is high, and that's when we want this one to be high too. Next, whenever we have the expectation operator in play, kind of, we need to make sure that this is not 0. So if P is positive, Q must be positive too. And then finally, there is no explicit relation to the entropy part now, because the entropy is with respect to P, which is given, and not with respect to Q, that is optimized. So slightly different ways of thinking. The main difference being this part here. If you go from Q to P, we need to make sure that Q is 0 when P is 0. Whereas when we go from P to Q, we swap this around and say that when P is not 0, then Q must not be 0. Okay? So this is the difference between the two. You can see that in the plot here, how they behave. So it looks like a kind of minor thing, right? Should I go from Kullback library Q to P or from P to Q? Can it be a difference? And the answer is yes, it can. We see here the Q to P one, the green line is more or less focusing on the most dominant mode and not caring at all about this guy. The moment projection, the P to Q one, is largering out its variance and trying to cover both modes. Zooming in on this area here, it's looking like this. So here we see the P to Q one is afraid of becoming 0 too quickly. So it's 0 avoiding. The information projection, or the Q to P, is, on the other hand, afraid of staying positive when the true distribution is quickly going to 0 here, therefore having to be low all over this second mode. So different behaviors. And then both can be used and both are used. But for variational, it is the information projection. So the Q from Q to P, that is the one that we work with. So this is the green one here. So the behavior is, as you can see, in the mixture Gaussian, it basically picks up the main mode. It's basically underestimating the posterior variance by going quickly to 0 because it's 0 avoiding. And this is, of course, the problem with that choice. But the positive thing is that we have a very efficient calculation of this, and we have a good interpretation through something called the ELBOW, evidence lower bound, that we will see soon. So that's our choice for distance function. We are going to do the Kullback library from Q to P. Yep. Yes. So this thing here is the correct posterior for the regression problem. And you will see in an example later today that the variational, or the one that we chose from Q to P, is going to kind of squeeze inside here. If you did it the other way around, the from P to Q one is going to be having a larger variance. So this is true. They behave differently in that way. And yeah, we should just be aware that this is a little bit sad, isn't it? We are trying here to be Bayesians and want to retain model uncertainty and all this, and then we make deliberate choices that are leading us towards an end result that underestimates the variance that we started out trying to capture. So we could have done this differently, and people do, but for the standard variational setup, this is how it's done. Maybe. So there's something called expectation propagation. That is the other way around. What do you say, Thomas? Have you seen people doing mix of both, like a symmetric KL thing?
Not a mix of both. They also have two quite different probabilities. I guess that's also one.
I'm going to entrust you with this one for the next time I can't answer the question. Okay. Yeah. Good. Yes. So let's see then how to solve this conundrum that we don't know the p distribution, but still we want to try to minimize this Kullback-Leibler. So there is some pencil pushing going on here, but this is not the worst slide that you'll see today, so please at least bear over me with me here, and then you can complain when we can come to the dreaded slide 19 instead. Okay, so the Kullback-Leibler is simply defined like this. The expectation under the first distribution of the log of the PDFs of the first divided by the second. So this is just the definition here. So what we do, multiply by P of D, the marginal likelihood or the evidence, both in the numerator and the denominator. So this is okay because it's just a probability, same probability, so we're multiplying by 1. Next, this guy here is not related to theta, so we're going to put it outside the expectation operator. And then on our way there, we are using that the log of a product is the sum of the logs. So we have log of this guy plus the log of the remaining part. Then the probability of P of theta given D times probability of P of D is of course just a joint, and here we are doing minus minus instead of plus, just to make it a little bit confusing, I guess. So this is also not magic. And then this part here, of course, looks a little bit messy, so we are just going to rename it. We are now calling that L of Q. And this is the elbow. If you heard about the elbow, this is the guy. So this is then defined simply as minus expectation of log Q over log joint P. And then here we are just swapping the numerator and the denominator and removing the minus sign. So this is the definition of elbow that we will use. Okay? So then, why is this cool? Why does it help us at all? Now, reordering the terms here, Kullback-Leibler is the evidence minus the elbow is the same as saying that the evidence is the elbow plus the Kullback-Leibler. This is kind of the insight that we need. And the clever thing now is to realize that this here does not depend on Q. Okay? So if I'm changing my Q distribution, my approximation, then whatever happens here needs to be reflected here. If this one goes up by something, this one needs to go down by something, or the other way around, because the sum is constant, right? So that means when I want to minimize this, I could just as well maximize that. The solution for maximizing the elbow is the same as the solution for minimizing the Kullback-Leibler. The value of the elbow is, of course, not the same as the value of the Kullback-Leibler, but the argmax of elbow maximization is the same as the argmin of the Kullback-Leibler minimization. Okay? So I can maximize this guy and be proud of my result, because that is the same Q as the one that would minimize the Kullback-Leibler that I set out to minimize in the first place. And this is doable, because here we have the log of the joint, not the posterior. So suddenly now I'm in a situation where I can calculate the terms. I couldn't here, but I can here. Okay? Oh yeah, yes, sorry. Why is it important that the elbow is a lower bound of log p? Well, first of all, why is it true? It is true because the Kullback-Leibler is non-negative, so it's a positive number or a zero number, so that means this one can never be larger than that one. And then if you think back to, say, maximum likelihood type, EM type learning, you always want to do something that you want to build a model that maximizes the probability of your data, right? So it's somehow related to that way of thinking here as well. We want to find a model that has a high elbow, and this elbow is related to this evidence. So we are kind of coming up with something of an argument that points in that direction. So this is kind of a sales pitch, I guess, for why elbow is a good property. So how I got to this thing. So this is the same as that product here. So, and I multiplied by P of D. I don't know what P of D is, but it is a number, and I'm multiplying both the numerator and the denominator in this fraction here with the same number. And the reason I'm doing that is because I hate this posterior because I can't calculate it, but I love this joint here because I can. So the problem is actually that this number is hard to find, but now I'm like getting rid of it. I know that it is bounded by my elbow, and I know that I can calculate my elbow, and I know also then that this P of D thing is something that I don't have to relate to anymore. So the whole point is this result that the maximization of elbow is the same as the minimization of the Kullback-Leibler between Q and the posterior. And that is kind of the point of this pencil pushing exercise. Good. So to summarize this now, we started off by choosing to minimize the Kullback-Leibler from Q to P, even though we know that this is somehow tricky and not optimal, in some senses at least. It was hard because we didn't know how to calculate this, because we didn't know what our target was. But then we found out that we could maximize the elbow instead of minimizing the Kullback-Leibler, and the result would be the same. So that is why then this is good. And then, as I said, the sales pitch here is that the elbow is a lower bound of the evidence, and therefore kind of fits with the way of thinking for learning. How are we on time, Thomas? Okay. So next question now is how to choose our set of candidate solutions. So this calligraphic Q thing. this is something that we also need to define before we can actually set out and do the calculations to decide what this Q of theta should be. And the way that we will do it is first by making what is called the mean field assumption, and then after choose distributions for simplicity. The mean field is basically just saying this thing here. The approximation is going to factorize. So it is a joint over many parameters, say the offset and the steepness of my regression line. And we know that this posterior for the fully Bayesian result there shows a negative correlation between the two. Then in the mean field assumption, I'm just saying I don't care about this correlation structure. I'm going to assume that my Q is defined as a product over marginals. All items are independent. They factorize according to this product. So this is, of course, wrong, and this is a problematic thing, but it's quick. So this is what we do. Mean field variational inference. Then, having done that, we can choose distributional families for each marginal. So in our regression example, for instance, I'm going to choose that each weight will have a Gaussian distribution. The joint is going to be the product of these guys. So then I need to find the parameters of each Gaussian, and then I'm done with my optimization. Okay?
Can you talk a little bit more about what that means for the data specifically? Are we assuming that the samples are independent from one another? Are we assuming that our models can't be related? What does this mean?
So when it comes to the data, we are kind of assuming that data points are independent of each other given the model, because we say that it's easy to calculate this joint here. So that's where this comes in. But if you can calculate this joint efficiently without making that assumption, then that's good. So what this thing here means is that I'm explicitly not considering distributions that enforce correlation between each of the parameters in my model. So while I know that, let's see, here I have the posterior over the offset and the incline, which shows a negative correlation here. The variational mean field thingy is just saying that we are disregarding that. So I'm not going to see ellipses that are skewed like this in the variational approximation. I'm going to see ellipses that has the main axis just as the coordinate system has. Good?
This mean assumption is also taken when the variation inference is applied to subsequent processes, because these inducing points are taken from the Gaussian process prior. So, and in the prior, the covariance matrix is not a diagonal matrix for the joint. So, so then also this mean field assumption is there, or is it not? Because when the inducing points, I believe they induce a multivariate normal that we try to approximate with the that we try to drive the posterior to approximate with that multivariate normal. So is that still there if we induce?
So do you then assume that this multivariate normal has a diagonal covariance matrix or not?
I mean the GP prior, if we put it such that the covariance matrix, the joint covariance, the covariance matrix of the GP prior would have non-diagonal elements also, because it will be a full rank
Okay.
covariance matrix. So is it still valid, this assumption, or is it not valid there?
You mean, is it still made or is it still valid? Because it's always wrong. So,
In the sense that, do we have to always do this, or is it that there are existing techniques that they don't do it over?
Yes, okay, yeah, so the question is if we always have to do the mean field assumption or not. We don't have to do it, and later today we will see something called black box where it's possible to not do it, so that's okay. First now we are doing the classic approach and doing stuff by hand, and then it's very hard if you don't do it, but still we can also do so intermediate versions where we have block diagonal matrices instead of diagonal matrices in the Gaussian setting, for instance. So that will be simplifying but not completely eradicating any correlation structure. Yeah. Okay. So the setup now, if we wrap it all up, is that our starting point was we have some data, we are able to calculate a joint, and we wanted to approximate the posterior. Then we chose Kullback-Leibler, leading us to the elbow as our objective. And now what we are going to do is to posit a variational family of distributions to each marginal. So as I said, I'm going to assume that each weight has a Gaussian distribution, for instance, and then the target is to find these weights here, or the parameters of that distribution here. And the way that we can do this is in this algorithm here, basically iteratively one dimension at a time. So what I'm going to do is to assume that, okay, I'm really happy with all my parameterizations except for one distribution, dimension number j. And then I'm going to optimize my dimension j given all the others. And then I'm going to change which one I'm optimizing until I'm optimized them all, and then I'm going to do that again and again until I'm happy. So this is the top-level algorithm for variational inference here. And we will see now what that means. But first, say sanity check. So what will the variational approximation look like here? The variational is given here with the green curves. So now I have sampled from the variational approximation given here with the green contour lines. We can see that we have lost the correlation structure. So the main axis of these ellipses are as the coordinate system, no correlation structure encoded. The covariance matrix here is diagonal. And we can see that it also is kind of smaller than the true posterior. We are underestimating the uncertainty we have in which model is the correct one. The behavior is given up here. We can see that samples of the offset, which can be seen here for x equals 0, is like smaller. The variation is smaller than it is in the true model. And we can see the lack of correlation structure by this like fan structure. Small starting points here, low samples of the offset, does not force me to have high values of the incline, so I can get lines that start low and get even lower, start high and get even higher, whereas I, for the true Bayesian, would have crossing behaviors instead. Okay, so these the offset and the incline here are independent in the approximation, and that's why we don't get this crossing behavior that we do for the true model. Good. Posterior predictive is more or less the same for the variational as it was for the Bayesian, so that's a good thing at least. More questions to this before we really start with the pencil pushing slide? Good. Yes, the reason why it seems here that, so we get this fan type shaped, right? And the reason for this is that the plotting, I guess. So a sample down here, low offset. If you do the, so that will be like down here somewhere. In the true Bayesian model, that will give me high probability of higher incline than usual. So that is a more steep line. But for the variational model, we will get the same type of inclines as if you had started somewhere else with a different offset. So that's why we get these crossing patterns for the Bayesian model and not for the variational. So for each point here, we get all the possible inclines. And this happens all over the place. So there are lots of crossing lines too. We don't see them. But what we do see here is the extremes that kind of span out this fan type structure.
I mean, that's my question. It would be possible that the model does not have heteroscedastic noise, but it might seem from the observation that right now we are able to visualize it, but if we are not able to visualize it on a plot, the true posterior.
So now you're talking about the posterior predictive.
I think it would be.
Yeah. I just don't understand what you're asking, I guess. So yes, the posterior predictive that is given down here for x equals 1 has a fairly large predictive variance, whereas if we chose it for 0, we would have a smaller predictive variance. Yes, yeah, now I got you, sorry. Good. Yeah, you should do some diagnostic. I'm going to convince myself it's not okay, but or it's wrong. But the main issue here would be the use case, I guess. So if you're like looking at rare events, what is the probability of crashing the tube towards the flight to the airport when you go home? Yes, this is unknown. What you know is that this is rare event things. It's not the correct approach to use this, because you are. We know that we are underestimating the uncertainty that the model has. So therefore, we are underestimating the tails of the predictive distribution. We are making it smaller than it should be. So if this is what you want, then it's bad. But if you want something that has more high probability region behavior, then this is good, or good enough, typically. But you should do use case driven testing with this. I'm just like trying to give a general answer so I don't have to come up with something clever. Yes, sorry. Yes, I know I shouldn't be better.
If a use case is suppose that we want to use a probabilistic model for optimization in a risky setting, so that we want to be risk averse, suppose in Bayesian optimization, would it be a wise choice then to use mean field assumptions for variational inference of our?
So a problem here is that the mean field is, so this taking out the correlation structure is forcing us to be even more condensed here in the posterior than we would have otherwise. So these things are kind of adding up to each other. I think if you really want to be risk averse, you would go the other way around and maybe do expectation propagation in this case. Well, Thomas is giving signals that I need to move on, so I'm going to do that. Okay, you remember this picture here. Our goal was to find the model among the candidates that was closest to our target. Now we decide what that means. We have the Kullback library here, or equivalently the maximization of elbow. And we have decided what it means to be in a set Q. We decide on the distributional families for each marginal, and the joint is going to be the product of the marginals. So that was now the setting. And now let's see how we can solve the elbow optimization analytically. So this is the dreaded number 19. I warned you all about it already. We will soon mix up and do some notebooks. So please stay patient. Okay, so we have this objective here. This is our elbow. This is what we want to optimize. We want to find the Q that has the highest elbow. And we are now going to utilize the mean field assumption by saying that the joint over all the thetas is the product over them marginally. Specifically now I'm interested in dimension j. So I'm taking that one out, and then I'm lumping the other ones together. This is true under the mean field, right? So I'm going to do only optimization on that guy. Assuming that these ones can be kept fixed, how can I do better on dimension j only? So I'm going to fix those, optimize that. Okay, so this is my plan. Elbow is this thing here. I'm just here using that the sum of the fraction is the, I get a minus here, and then everything is good. And from here to here, it's the mean field. The expectation over all of the variables in Q is just the expectation over the variables except j, and then the variable j after, since the mean field assumption is made. Okay, and then let's look at this part. It looks nasty. So again, we are going to do the representation trick or notation trick. I'm just like inventing a new letter for stuff that looks difficult. So now, this is an expectation. It's a real number. I'm going to assume that there is a wiggly f function that is so that the log of it is this number here. I'm not making any assumptions basically here, because this can always be done. Since this is a real number, there is an f that fits. This is a function only of theta j, because I'm doing the expectation operator over all the dimensions except j. So they kind of disappear. The only moving part in this thing here on the right-hand side is theta j. And now I define the result here through this wiggly f thing. So that's step one. And then step two is to say that I like it even better if I can normalize this thing. So this fj with the tilde on top, normalized, so divided by the integral, is now defined as this f without the tilde. Okay? Why not? So this is now my function, and the relationship between this and that is that this f log of it is that thing plus a constant. So I'm going to replace this one by that thing. And that's what happened here. Now, this part. Here I get to use my mean field assumption again. So, log of joint is log of dimension j plus log of the rest. This is the mean field. Here, expectation of sum is sum of expectations. From here to here, we are utilizing that this guy here does not depend on the other dimensions, so just removing that expectation operator. And for this thing, it does not depend on theta j, so remove that expectation operator. So now we are here. And then finally, this last part is just a constant when seen as a function of theta j. It's just a number, right? Call it C2. So then, this double expectation is just that expectation plus a constant. Like this. And now we are almost there. So let's look at what we have. We have expectation under qj of this log f function minus the expectation under qj of log of the density itself, plus a constant. Now, these two guys can be, per definition, written out as the Kullback-Leibler from q to f with a minus in front. This is legal because we made f so that it is always positive, and so that it integrates to 1. So why not pretend it's a distribution suddenly? So now we can just replace this part by minus Kullback-Leibler from Q to F. And that's what happened here. So all of this now means elbow is a constant minus this Kullback-Leibler here. Okay? And that's basically the result. Because we want to maximize this, that means we would like to have this one to be 0. It's never negative, so the best we can do is to have it at 0, since we are subtracting. And then, how do we get it to be 0? Well, we choose this one to be identical to that one. This is the only way that the Kullback-Leibler can be 0. So that is the result. We need to choose Qj equal to Fj. So tracing back and finding out what Fj was, this is the thing that we end up with. Which was a little bit of a nasty pencil pushing exercise, I agree. But the result anyway is Qj, this is a distribution function that looks like the following. It's e to the power of some expectation that is given by the other Q distributions that we have at this point in time, and then normalized. Looks like we haven't really gained anything, but the trick here is we are free to choose distribution family for this guy here. So if we choose that one to be, say, Gaussian, and that fact actually works, then we can calculate this stuff here and recognize the parameters that fit with this Gaussian in a good way. So basically here, this is a result that holds, and sometimes it's useful. We use mean field to get there, and then this coordinate ascent way of thinking, fixing all parameters except j, optimizing the distribution for j only. So that was the result there. Okay, so we had this here already. Our setup was that we wanted to find this posterior by choosing variational families and then making the approximation by multiplying these guys when we had optimized them separately. And now we have the Kavi algorithm where we basically know how to do it. So what we will do is to go through each dimension, calculate this thing here. Even though it looks bad, it's not always that hard as it's not as hard as it seems sometimes, and then those times we are golden. Then we optimize the distribution and by utilizing this relationship that we just found, and then keep going until it has converged. And when I say until it has converged, the cool thing here is that it's guaranteed to converge, and sometimes, in particular when we have conjugate exponential family distributions, and we will not really talk about that, but anyway, I just put it in there anyway. We are guaranteed to find the one distribution that is closest to our target, even though we don't know what the target is. So this is kind of remarkable, I would say. Yes, so sometimes this folds out very nicely. Many times it doesn't, but you will see pencil pushing example soon, where it actually, in the notebook that you will implement, you will have this working out nicely. So in the regression model problem, it was very nice. And for basically for conjugate exponential family distributions, if you know what that would mean, then it works. Because you stay inside the model class and you can just pick the parameters by recognizing what they should be. But in general, this is hard. Yeah?
Is maximizing the course to maximize the log likelihood of the dataset?
Is maximizing the elbow the same as maximizing the log likelihood of the dataset? It's the same as maximizing this lower bound of the log likelihood. So that's why I said that this is a sales pitch for the elbow, is that it has a relationship to the log likelihood of the data set.
It's not guaranteeing we can maximize that.
So it's guaranteeing that it's maximizing the lower bound, so it's kind of pushing this.
Another question, why do we want to maximize the log likelihood of the dataset?
So what we do here is to combine something that is related to, why do we, I need to repeat for the camera or the tape. So why do we want to maximize this log likelihood? Or the elbow in this case. So what we do now is that we are taking two sources of inspiration for choosing our parameterization. One is the prior, and the other is the desire to make something that can produce the data that we have. If you have a model that gives your data a very, very small likelihood, it means that this is a poor explanation for why the data is like it is, right? So this has kind of the argument would be that, okay, my model here is plausible given the data that I have and the prior that I have. Yes?
Just going back to the example, let's say I've restricted myself to Gaussian representation. I might not be able to find a parameterization that is proportional to this explanation. Right?
Yes. So this is why I'm making this conjugate exponential family requirement. Then if I start with a prior that has some meaning, then this is going to stay within that class when I observe my data, and then it's going to fall out nicely. Yep. Good. How are we on time, Thomas? Okay. So yeah, I'm just like thinking, should we just disregard questions? We are losing our break. I don't know if we should. I'll finalize my slides. Then, if you have questions, come in the break. Okay. Good. So here is just the final slide. It's a movie of what is going to go on. So we have a setup where we are optimizing the distribution for the offset, W0, and the incline, W1, in this regression model, step by step. The true posterior is this blue thing here, and we will see that it's kind of moving towards that in an incremental way, optimizing each dimension in turn. And this is the behavior that we force upon it by this coordinate descent way of thinking. So assuming that the offset is correct, what would the best incline distribution be? Assuming that the incline distribution is fixed, what is the best offset distribution, and so on. This is how we swap back and forth, as you can see here, when the distribution is moving towards the target and ending up with this model that is assuming independence and is underestimating the posterior variance. Okay, when is the break supposed to be over? Now? Okay, so should we just break? We have break until 10:30. I'll answer questions while we have break, and then you can go out and have break if you want, or you can be here and ask questions if you want.
So welcome back from the break. Before we get started on this last part here before lunch, then just a quick update here. We are going to mix slides and exercises for the remaining time until 12 o'clock. So we won't have any dedicated breaks, but obviously during the exercise time you are welcome to go out for a bio break or coffee or whatever. But it's sort of going to be a bit more of a mix now. So what I'm going to focus on now is to illustrate with an example some of the concepts that Helge introduced just before the break. So we spent quite a lot of time on pencil pushing and deriving sort of the general updating rules for doing coordinate variational inference for general model classes. And what we'll take a look at now is to see how this is actually, what kind of form it takes for a very simple type of model, in this case here, a simple Gaussian model. Promise we won't stick to these very simple models all the way through today. We're also going to be a bit more general, but taking baby steps. Afterwards, we're going to look at linear regression models again and look more closely into that. And then later on, we'll take more complex model classes. So, but that's sort of after the lunch that we're going in that direction. So for this part here, we'll be looking at this simple Gaussian model where we have a collection of random variables x that are normally distributed, and we also have observations of those. They're normally distributed with a mean mu and a variance that's defined by precision, so the inverse of the variance. In this case here, the precision is gamma. Both mu and gamma are unknown parameters. Mu is given a normal distribution that is centered around 0, and with a precision of tau, again, that would be the inverse of the variance. And gamma is distributed with a gamma distribution with a shape and rate parameter alpha and beta. And here we have to the left the plate notation of this model that Celia and Andrew also showed you yesterday. And if you take this model in the plate notation and write it up, then we have an expression that looks something, a factorized form that looks something like this, where we have our data, calligraphic D, mu and gamma. Mu and gamma we are collectively calling theta, so these are the parameters that we're interested in calculating a posterior distribution over. And then we have 8 n data points, where we have our likelihood term here multiplying, and then we have our prior terms for our unknown parameters. We are going to stick with the assumptions that Helge introduced. So we are going to assume do variational inference under the mean field assumption. So we assume that our variational posterior distribution over mu and gamma factorizes into a product consisting of a variational distribution for mu and one for gamma. And again, our variational objective is to minimize the Kullback-Leibler divergence between our variational approximation and then the true posterior defined by our model P. And this is going to be achieved not by optimizing the KL directly, but rather going through the elbow, as we talked about before. And we also assume here that very conveniently, that our variational posteriors fall in the same model classes as our prior distributions. So we posit this general class of distributions where we assume our variational distributions live in. So for mu, we assume that the variational posterior is also given by a normal distribution with some variational parameters to be optimized. And for gamma, we also assume a variational posterior, in this case here, a gamma distribution, also given its own set of variational parameters to be optimized. And again, notice here that they fall into the same model classes as the priors. So that's sort of our general setup for the model class and the variational component. What we will try to do now is to do, for this concrete example here, a bit of pencil pushing again, but arriving at an updating rule for what does the variational distribution look like for this particular model class. So illustrate the general calculations that Helge went through just before the break. So we have here that the general expression that Helge came up with was that if we are looking for the variational distribution of Q, then it should be that the log Q would be the expectation with respect to the log of the joint over the data and our two variational parameters plus some constant term. So this is sort of what we started off with before the break, that this is how we set our variational distribution. And now we are sort of going to unfold it a bit based on this particular model class and then see what kind of form that it takes. So the first thing to notice is, again, here, this is just a recall of what kind of model that we are currently looking at. We had the log of the distribution defined by the model. So the log of a product is the sum of logs. So we have a sum over our data points here, log of the likelihood terms plus log of the two prior distributions that we have. Since we are looking at this part up here, so log Q of mu, we are only interested in the components that involve mu in some way. So that means that if we are looking at the expression down here, then mu only appears in this part here and in this part over here. So we single these two guys out, marking them down here with blue, and putting them up here. So we are just moving the blue part up here, and then we have sort of this constant term here. And this constant term is going to be a garbage bin where we are throwing all the terms in that does not involve mu. So in principle, the C that you see here is different from the C that you see here, but in order not to introduce too many indexes and the like, we'll just use the same C throughout. Then, if we look at what the form that these two distributions take, both of them are normally distributed. And if we write it out, so we have the log p of x, the likelihood term here, normally distributed, taking this form here, and log p of mu, again normally distributed, and taking this form here if we write it out. And again, we can single out the components involving mu. And that means that we can actually throw away these parts here. They're just constants in this context here, and focusing on the two parts that we have here over here. So we now put that in. So we have a contribution from this part here. That would be this that we have over here. And for this, we have tau divided by 2 multiplied with mu squared. And that is this part that we have over here. Next, we just expand on the square that we have here. So we have xi minus mu squared. So that will give us xi squared. We have a mu squared, and then 2 mu xi. And then we also have we have a gamma divided by 2 here. So we have a half out here. We have gamma gamma out here, where we are taking the expectation. So the expectation of this expression here only involves gamma. So this is just the expectation of gamma that we have here. And then we have the sum that is also being moved out into this expression. So the sum over xi squared. We have n terms in total. Mu does not depend on I, so that will just be n mu squared. And then we have the expression here again with the xi's. This part here is the same. Next, we are going to just shuffle a bit of stuff around. So let's isolate the parts that involves mu squared. We have a mu squared that appears here and a mu squared that appears here. We'll collect that down here. So we have mu squared times tau. That is for this part here. And we have mu squared times the expectation of gamma multiplied with n. That comes from this guy that we have here. The expectation over gamma is out here. And then we have another term where we isolate the parts that just involves mu. And that is this expression that we have here. And this is repeated down here. Now, the reason why we do this, well, okay, what happened here is just that I took this here and moved it up, so I just deleted these 2 lines. That's the only thing that has happened here. And the reason why we have shuffled terms around and isolated parts that involve mu squared and mu, that's because that if we write out if we assume that log of q follows a normal distribution, what kind of form would it take? Well, if we write it out, so this is the log of the normal distribution, focusing on the parts that involves mu. So that is just this part over here. And if we expand on the square, then we'll have something where mu squared appears and mu appears over here. And that means that we can do a bit of pattern matching here. So we can match up this part here with mu squared to the part up here where we see mu squared. And here we have mu, and we can match that up to the mu part over here. So a bit more explicitly, the red part goes up here, and the green part goes up here. So we are just sort of aligning terms, basically. And then we can sort of read off what should the precision, what should the mean actually be for this. Well, down here we can see that the precision tau that we have here, that is the part that goes together with mu squared. Okay, what do we have up here? We have this expression up here multiplied with mu squared. So this here will be the precision for the variational posterior that I have calculated for the model. And I put that here, so that's tau q. And I also have this part down here. So nu that I have here would be the mean. And the part that is multiplied on the mean here would be the precision and mu. and we have mu up here, so that means that the mean value for our variational posterior, nu that I have here, can be directly read off this expression up here by simply aligning this part here with this part. I'm multiplying with the inverse of tau here, because I have tau down here, so they cancel each other out. And that means that nu that I have here corresponds to this part here, multiplied by tau in -1. So what we tried to show you here sort of was the steps that you would have to, or you can go through in order to figure out for this particular model here, what would be the variational updating rule for Q of mu. So we can do this in closed form by, in this particular case here, by cleverly choosing what kind of variational distribution that we want to work with and matching that with the prior distributions that we have up here. We can do the same thing for for gamma. So here I spare you for all the pencil pushing, but the steps are basically the same again. We are aiming for a variational distribution that is gamma distributed, and then you can write out all the steps before and recognize that eventually you end up with something that looks like a gamma distribution. And if you do that, then you'll find that the shape parameter for your variational posterior distribution will take this form here, n divided by 2 plus the shape parameter for your prior, and the same for the rate. You have this expression here giving you a rate parameter for your variational posterior. And for calculating this part here, the beta part, we have a sum over an expectation over xi minus mu squared. How do we calculate that? Well, here are some sort of quick steps to go through here, so we can expand on the square here, get this expression xi squared, and then you have expectation over mu squared, and then you have an expectation over mu. So this part here is just given from your variational posterior that we just calculated. That would be the mean value. And for calculating the expectation over mu squared, well, that's just equal to the variance of mu, which we found before, and the expectation over mu, and then squaring that expectation. So here again, we have a closed form updating rules for finding the variational distribution over gamma in this case here. And again, this works for this particular model class that we have. I hope that you can appreciate sort of the updating steps that we went through here, and sort of the only trick that we did was to do basically pattern matching between the prior and the variational that we were looking for. For this particular model class, we can also write out the elbow in closed form. So if you, here we are just having the expression, we have the expectation over the log of the distribution defined by the model, minus the expectation over the log of the variational distribution, which would be the same as adding up the entropy over that distribution. And if you use the factorization implied by the model that you have down here, then we end up with an expression looking like this. And when you can do this, this is actually quite convenient, because then you can use the elbow, which we are optimizing in a coordinate ascent fashion by iterating through between updating the gamma distribution that we have here and updating the normal distribution over mu that we have here. And sort of these are done alternately, because here we see that the variational distribution over mu depends on the distribution over gamma, and the variational distribution over gamma depends on the variational distribution over mu that we have here. So we are optimizing the elbow in a coordinate ascent fashion, alternating between these two updating steps. And we are guaranteed through this that the elbow that we're optimizing will always increase. So we will never see a decrease in the elbow. If you do, you have a bug in your code, or you have done something wrong with your derivations. So this is also what this type of, if you have these constraint models, which make it quite nice, because you can really use the elbow here, visualize it, and use it for debugging your model when you're doing that. And this may come quite in handy for the first exercise that you will be working with here, because now you're going to get a bit of grease on your fingers. We have on GitHub some notebooks. The first one is the one called Student Simple Model that you see here, where we will start by playing around with this very simple model that we have here. And you'll get a chance to implement updating rules for these variational distributions, and also play a bit around with both the variation with the model in itself, maybe the prior distribution that you put on the parameters, also the data sizes, just to see sort of the effect of what happens when you change these parts of the model. So let me just give a quick introduction. So if you open the notebook, we just have the slide here with the specification. We install everything here, and we have a specification of the parameters that goes, the prior parameters that goes in. So here we have alpha prior and beta prior that goes to defining the prior distribution over gamma, the precision for our normal distribution over the variables. And we have mu tau and mu prior and tau prior, so that would be the distribution over mu that we have here. And the prior is assumed to be 0, and the precision is assumed to be very small, so we have a very large variance, so it's very uninformative. 100 data points that is being sampled from a normal distribution with a mean of 5 and a precision of 1. Sort of this is our data set. Then we have a few helper routines. We have something for doing plotting of the densities. Not that interesting here. Then we have a routine for calculating the elbow, so you don't have to worry about that. So it takes the standard parameters in, so you have the data and the parameters for the prior distributions and for your variational. And here we then have a specification of the elbow calculations that you can also take a look at during the exercise time. Then for doing the variational base that we have here, this is just a slide put in where summarizing the updating rules. We have the updating rule for mu up here, and we have the updating rules for gamma down here. And then with these components here that you may find useful. And then we have everything implemented here. So we have a bit of initialization of our parameters up here, our variational parameters, and all our variational parameters here are, have a subscript q associated with them, so they're just assigned, initialized with the priors. And then we have the updating rule. This here is the updating rule for gamma, and you can see that it's a bit incomplete, so alpha q is just set to 0 here. We have beta q has been defined, so you don't have to worry about that. And here we have for the updating rules for the variational distribution over mu, where again you need to go in and fill some blanks here. And if you do that, and when you've done that, then we are iterating, we are doing 1,000 steps, and then we are keeping track of the elbow, and then maybe also printing out of a bit of debugging information here. For instance, the elbow should always increase. So you can again use this here to debug your code and your derivations. And if you do that here, then if you just run it as it is, then this is what you get. And you can see there are some values here that doesn't make sense, but that's because that we haven't implemented the updating rules yet. And then down here, there's a bit of a test where you can plot the densities that you calculated. Not very informative at this point here, but that's also for getting a bit more insight into the model. So this is the setup for now. So we have a small exercise session where you can play around with this and try to get a feel for these updating rules and how they actually behave in the code. And I can't quite recall how many minutes we set aside, but maybe 10, 15 minutes. And So time is running, so unfortunately we'll have to end the exercise session now. There will be several more exercise sessions, and there will probably also be a bit of time for you to go back to this if you want to have a closer look at it and haven't finished. We'll also put up the solutions on the GitHub page after today, so if you didn't finish and you want to play around, then you can try to do that. Maybe just a couple of points to make here in the updating equations. You have, for instance, here alpha q. It's actually just set once. It doesn't depend on the other updating rules that are being made, so you just need to have that fixed once. So n half plus alpha. Alpha would be the prior parameter that you have in for your model. Also, when you so here this is the solution where we have made the full implementation. And when you have run this, you will see the convergence within a relatively short number of iterations. And for playing a bit around with the effect of changing the priors, changing the amount of data, where you can look is in the plots that we have made down here, where you can see this is sort of the plot for the prior distribution that you have over the parameters, not particularly interesting. This here is the posterior distribution that you'll get if you run the code here. So first of all, one can notice that you have independence between the precision, or that the joint distribution factorizes. You're assuming posterior independence here between mu and gamma. And we have sort of the correct value here, that's the blue dot. And then we have sort of the contour plots for the density, the posterior variational density. And then you can try to play around with the prior distribution and the amount of data that you have and see what kind of effect does that have on your variational posterior distribution. Good. So what we will be looking at now is linear regression again. So at some point we'll get to the more fancy models, but we are not quite there yet. But we'll still take a slightly deeper dive into Bayesian linear regression and to see what that can be used for, also to provide you with a bit better understanding of what are the consequences of the assumptions that you're making with the variational inference, like the mean field assumption, but looking at it from let's say a true data set, using a true data set. So the data set that we'll be looking at here describes the relationship, or is data about the GDP of a country, actually the log GDP, and a measure called the terrain ruggedness index here. So basically a measure of the geography within a particular country. And the data is divided so that you have something about data for countries outside of Africa, so non-African nations, and data for African nations. And there is expected a relationship between the terrain ruggedness index and the log GDP of whether it's African and non-African nations. And at first sight, if you just do linear regression, one would get results looking like this. So you have a regression line here, you would have a regression line here. But the question would then be, is this really supported in the data? That you see an inverse relationship depending on what, whether it's African and non-African countries. So in particular, considering that we have a rather limited number of data points here, or 170 or so. So this is what we'll try to look into here with a Bayesian linear regression. So the model that we are going to put up is this guy up here, with this formalized over here. So we have our response variable yi, that would be the log GDP of the country. We have b here, that's an explicit bias term or offset. We have sometimes also described that as being another weight parameter that's just multiplied with 1, but we've singled it out here as a bias term. And then we have a weight vector here, and in this case here, the vector would actually be a scalar because we're only looking at the terrain ruggedness index. So in terms of the dimensionality up here, we have n data points, and the number of attributes, predictor variables that we have here is denoted by m, but m in this case here will just be 1. So this is sort of a slightly more general form of our linear regression model. And then we assume uncertainty. We assume that we are uncertain about the bias parameter or offset, and also the incline, the slope that we have over here. But we assume that the uncertainty, the noise associated with the response variable, and that would be theta in this case here, and that's sort of the precision, that is assumed to be unknown, but we are not giving it a distribution. So if we wanted to estimate this from data, we would do maximum likelihood estimation that Celia talked about yesterday, but for now we are just disregarding it and assuming it to be fixed. And we can, this model here then defines or implies a factorization form that we have here. And again, we'll be, after taking the log, we have this expression here that we're also going to use when we do our updating rules. And we can also specify our variational distribution. And this is again assuming a mean field factorization. So we have a posterior variational distribution over the bias term, and we have a posterior variational distribution over the incline. And since we only have one of these weight parameters, the incline, that means that this m here is actually just 1. So there's not really a product going on. But this is sort of a model for a full Bayesian linear regression that you can use if you have your own data set that you would like to play with at some point. The updating rule, and here we'll spare you all the details. The slides include supplementary material, so if you want to verify what the updating rules are actually, how they're derived, you can go into the supplementary material at the end of the slide set. But otherwise, cutting it a bit short, then we assume that Q, the variational distribution over the weight, is normally distributed with a precision taking this form here and the mean value taking this form here. And again, all the details are in the supplementary material. And B, the bias term, is also normally distributed and have these two updating rules. And you can again see that they are coupled together. So here we have the expectation over the weights for the updating rule for B, and for the updating rule for W, we have the expectation over B here. So they are mutually interlinked. So, and in the supplementary material that you can find everything here. What we will focus on now is a notebook illustrating all this. So, and it's also on the GitHub repository for you to play around with. So what I'll be doing now is just to give you an introduction to the notebook, and then the time until the lunch break will be for you to play around with the notebook, not really doing so much coding, but more playing around with the models and the updating rules to get a better feel for what's actually going on. There's a bit of background on the data set that we have here, if you would like to dig into that. Here we are loading the data, and the only thing to notice here that might be worth is the way that we organize the data. So we have the predictor variable X and the response variable Y, and these two are given as dictionaries where we have one component for non-African nations and one for African, and then it goes both for the predictors and the response variable. We have 170 countries in total. And this is the type of data that we have. So we are only interested in the ruggedness index here and the log GDP over here. Then we have prepared a bit of code for doing plotting. So this is just for some helper functions, not that interesting here. So this is a scatter plot of the data that we also had on the slides. Then we are going to play around with different subsets of the data here just to see the effect of changing the amount of data that's actually being used. So this is a helper function for doing that. Get data subsets. Again, not that particularly interesting. Then there's something we want to visualize the models that we learn. And this is just a helper function for doing that. It's not something that you really need to dig into at this point here. It's just to let you know that it's here. For comparison, we are also going to do standard linear regression. So it will just be standard linear regression where we add a bit of noise out here, epsilon. And the model that we set up is defined using PyTorch. So we, for those of you who know PyTorch, you've probably seen this many times before. Otherwise, for those of you who don't know it, this is just one way of specifying the model, the linear regression model here, where we have some parameters specified up here and the relationship down here. And I'm going to be lazy and just use PyTorch also for doing the learning, and we are just finding a least square solution. And if we do that, then we get these solutions here, and this corresponds to what I showed you on the slides also. So we do learning for non-African nations and for African nations. And we have our learned weights here. The first components in both of these vectors here correspond to the offset. And the next one is the incline, where you can see that the sign on the inclines here have been swapped. You have negative for non-African and positive for African nations. Here I'm using my helper function for plotting the model or showing the model. So these are the results that we get. And plotting out the information that I just told you about before. Then one could look, for instance, into what is the effect of adding outliers. So we have 170 countries in the data set as a whole. So what if we just introduce a bit of noise here? And what I'm doing here is to add two artificial countries to the data set for African and non-African nations, and learning a new model again. And just to show you what it looks like, we have that here. So the colors may be a bit unfortunate, but we have a green dot here and here. So these are artificial countries that I have introduced, and we have the same thing down here. And you can see that by just introducing two artificial data points here, we actually see quite a difference in the behavior of the models that we are learning here. So they have really a big impact on the solutions that we end up with. So that's also something to keep in mind when you start to play around and analyze the model, that the effect of having outliers and limited data. And we can again get our slopes here, and now we can actually see that by just introducing these two outliers here, we suddenly have the same sign on the slope for both non-African and African nations. But we want to do this sort of in a Bayesian setting. We want to express the uncertainty that we have about the domain and the models that we are learning. And we are going to use the model that I just showed you before, illustrated here, but now again keeping in mind that this specification here is for general Bayesian linear regression, but which also means that we may have a weight vector with multiple parameters, but in our case here, the number of parameters, the components, is just one. So M here is just one in this case. We have also made it a bit easy here to estimate to monitor the convergence. So we have specified the elbow calculations here, and you can go in and check whether it also makes sense or try to follow the derivations here. It's not something that we have paid that much attention to in the slides, but here you have sort of a more meticulous example of how this can actually be done. Our variational solution, we assume mean field factorization, and again for our simple case it just means that we have this factorization of our variational distribution. We have our updating equations, so this here we're updating W, the incline. Again, when you read this, look at the code here, again important that this is for the general case. So we, for instance, have set up here that we can, when we specify the updating rule for W here, we can update each of the components in the weight vector. Which component to be updated here is given down here, the weight component to be updated. That will always just be one. So just keep in mind when you read it, it will make these, the reading much easier. And down here we have the updating rules for B. And also please check whether the updating rules here actually links back to the slides. Hopefully they should. At least we get the right behavior in terms of the elbow. And here we have sort of the do the variational base. We have our variational solution specified here, and we are just doing it for each, both African and non-African countries. We do a bit of initialization of our variational parameters, and then we are iterating here for 100 iteration, keeping track of whether the elbow is increasing as it should, and so forth. And here we learn our model with the data set that we have. So again, for the non-African and African nations, and the elbow should be increasing all the time, and this is sort of the plots that we get. And we can also play around with a bit of visualization here. So here we are doing the same stuff that Helge showed you earlier. So we are taking the variational posterior distribution over the bias and the offset, and then sampling 100 points for this variational posterior, each corresponding to one of the lines that you see here. And this is sort of also a reflection of the uncertainty that you have in the domain. Again, notice here that the lines are sort of not crisscrossing very much, which is also an indication that we assume that the variational posterior factorizes. Since this is just linear or Bayesian linear regression, we can also do exact solutions. So we can actually find the exact Bayesian solution, and this is sort of what you can find here if you take a closer look at the updating rules that have been implemented here. But this is just a full Bayesian solution that you go through. And we can find that here, and we learn the parameters, and these are the results that we end up with. And we can do a bit of evaluation here. So this is from the Bayesian. Now we are sampling from the Bayesian solution, just as we did before. And now you can again see these crisscrossing of some of the lines here, again indicating that these two components, the bias and the incline, are negatively correlated. A high bias term would correspond to a lower incline, and so and vice versa. And here it's just for comparison again with the variational, where we can see that this is not really reflected in the plots. Then a few more helper functions for doing visualization. Density plots. So these are sort of the contour plots for the posterior, both the exact Bayesian, which is the blue part, and the approximate variational with the mean field assumption, which is the green part here. And we can also look at the marginals. This is what you have here for non-African nations, African nations, bias up here and slope down here. And what you can also see here is that we consistently underestimate the variance. So the variational posterior is the blue one, and the true exact one is the orange one. The posterior predictive distribution can be found by taking the posterior distribution of the weights, and now here I'm just been lazy. I also included the bias term, so everything here is within the weight vector, and then multiplied with the likelihood model that we have here, and then you can find the posterior predictive distribution over your response variable. This is what we have calculated here, and you can then play around with that and visualize it. This is what we have here. So this here is for the posterior predictive distribution for the base model. If you want to see it for the variational, you should just change the model here to model variational instead. But this is sort of the expression of uncertainty that we have here. So this here is the aleatoric uncertainty, so the uncertainty in the response variable, plus 2 standard deviations around the mean value. And this is sort of what the purple area here indicates. And here you can also see that we are pretty uncertain about the correct predictions. And we can also calculate the log likelihood of the data given the model for model comparison. And that then leads up to the exercises. So here, for the next half hour, this is basically free time to play around. So it's here you have some stuff in the notebook that you can work with. We have tried to set up some demonstrations or solution templates that you can, for you to get some easy hands-on experience. There's something about here changing the prior distributions of the model. What kind of effect does that have in terms of the estimates that you get, and also in the posterior predictive, experimenting with the amount of data that is being used. So if we vastly reduce the amount of data, what does that then imply about our predictions? And here we can also have code for varying the amount of data that is being used during training. So you can see, okay, what if you gradually increase the amount of data? What kind of impact does that have? But that is for you to play around with.